NENOMATICA, where mathematics meets YouTube excellence. Welcome to this lesson on the sum of coefficients in a polynomial. Today we're going to learn an elegant technique to find the sum of all coefficients in a polynomial without having to add them up individually. Let's start with a general polynomial p of x, which can be written as a 0 plus a 1x plus a 2x squared plus a 3x cubed, and so on. The coefficients of this polynomial are a 0, a 1, a 2, and so on. Here's an important property. When we substitute x equals 1 into the polynomial p of x, the result is the sum of all coefficients. Let's see why this works. When we substitute x equals 1 into our polynomial, we get p of 1 equals a 0 plus a 1 times 1 plus a 2 times 1 squared plus a 3 times 1 cubed, and so on. Since any power of 1 equals 1, this simplifies to a 0 plus a 1 plus a 2 plus a 3, and so on. This is exactly the sum of all coefficients in the polynomial. This property extends to multivariate polynomials as well. For a polynomial p of x, y, z, and so on, the sum of all coefficients equals p of 1, 1, 1, and so on, where we substitute 1 for each variable. Let's look at a simple example. Consider the polynomial p of x equals 3 plus 5x plus 2x squared. To find the sum of coefficients, we evaluate p at x equals 1. P of 1 equals 3 plus 5 times 1 plus 2 times 1 squared, which gives us 3 plus 5 plus 2, which equals 10. So the sum of coefficients in this polynomial is 10. Let's try a more complex example. Consider the polynomial p of x equals 4 minus 3x plus 7x squared minus 2x cubed. Again, we substitute x equals 1. P of 1 equals 4 minus 3 times 1 plus 7 times 1 squared minus 2 times 1 cubed, which equals 4 minus 3 plus 7 minus 2, which gives us 6. Therefore, the sum of coefficients is 6. Now, let's look at a multivariate polynomial example. Consider the polynomial p of x. Y equals 2 plus 3x plus 4, y plus 5xy. To find the sum of coefficients, we evaluate p at x equals 1, and y equals 1. P of 1 equals 2 plus 3 times 1 plus 4 times 1 plus 5 times 1 times 1, which equals 2 plus 3 plus 4 plus 5, giving us 14. So the sum of coefficients in this multivariate polynomial is 14. In this video, we'll learn an elegant method to calculate the sum of coefficients quickly. One of the most elegant properties in polynomial mathematics is that the sum of all coefficients in a polynomial can be found by evaluating the polynomial at x equals 1. Let's see why this works. Consider a general polynomial p of x. A sub nx to the power n plus a sub n minus 1x to the power n minus 1 plus a sub 1x plus a sub 0. When we evaluate this at x equals 1, all the x terms become 1, and we're simply left with the sum of all the coefficients. Let's look at our first example. We have the polynomial p of x equals 5x to the power 4 minus 2x cubed plus 3x squared minus 2x minus 7. To find the sum of the coefficients, we need to evaluate p of 1. Let's substitute x equals 1 into our polynomial. Now, let's simplify this expression. Any number raised to the power of 1 is just the number itself. Let's calculate the final result. We have 5 minus 2 equals 3. 3 plus 3 equals 6. 6 minus 2 equals 4. 4 minus 7 equals negative 3. Therefore, the sum of the coefficients in our polynomial p of x equals negative 3. Let's move on to our second example. We have the polynomial q of x equals 5x squared minus 7x plus 1, all raised to the power of 20. Again, to find the sum of all coefficients, we evaluate q of 1. Let's substitute x equals 1 into our expression. Let's simplify the expression inside the parentheses. Now, we need to determine the value of negative 1 raised to the power of 20. Since negative 1 raised to an even power is 1, and 20 is an even number, the result is 1. Therefore, the sum of all coefficients in q of x equals 1. To summarize, we've learned that the sum of all coefficients in a polynomial can be quickly found by evaluating the polynomial at x equals 1. This works because when we substitute x equals 1, all terms become 1 to some power, which is just 1. So we're left with just the sum of all the coefficients. We have a function r of x and y defined as 2x minus y, multiplied by the quantity x squared plus 4x y plus 3y squared. We need to find the value of this function when x equals 1 and y equals 1. Let's evaluate this step by step. First, we substitute the values x equals 1 and y equals 1 into our function. The expression becomes 2 times 1 minus 1, multiplied by the quantity 1 squared plus 4 times 1 plus 3 times 1 squared. This simplifies to 2 times 1 minus 1 times the quantity 1 plus 4 plus 3. Let's simplify this further. The first part, 2 times 1 minus 1 equals 1. The second part, 1 squared plus 4 times 1 plus 3 times 1 squared equals 1 plus 4 plus 3, which equals 8. So we have 1 times 8. So our final answer is R of 1, 1 equals 8. Now, let's look at another example. We have a function f of x, which is 5x cubed minus 2x squared minus 3x minus 1, all raised to the power of 32. We need to find the value of this function when x equals 1. Let's evaluate this step by step. First, we substitute the value x equals 1 into our function. The expression becomes 5 times 1 cubed minus 2 times 1 squared minus 3 times 1 minus 1, all raised to the power of 32. Now, let's simplify the expression inside the brackets. 5 times 1 cubed equals 5. 2 times 1 squared equals 2. 3 times 1 equals 3. And 1 is just 1. So we have 5 minus 2 minus 3 minus 1, which equals negative 1, all raised to the power of 32. Let's simplify this further. We get negative 1 raised to the power of 32. Now we need to evaluate negative 1 to the power of 32. When we raise negative 1 to an even power, the result is always positive 1 because the negative signs cancel in pairs. Since 32 is an even number, negative 1 raised to the power 32 equals 1. As we've seen, evaluating functions involves carefully substituting the given values and following the steps of calculation in the correct order. For our first example, we found that R of 1, 1 equals 8. And for our second example, we found that f of 1 equals 1. We need to evaluate the function f of x equals x to the fourth power plus x squared plus 1 at x equals square root of 2. Let's substitute x equals square root of 2 into our function. Now let's simplify each term. For the first term, the square root of 2 raised to the fourth power, we can think of this as square root of 2 squared, squared again. Square root of 2 squared is 2, and 2 squared is 4. Next, let's simplify the second term. Square root of 2 squared is equal to 2. Finally, we add all the terms together to find the value of the function. For plus 2 plus 1 equals 7. Now, let's move on to the second example. For this problem, we need to find the sum of coefficients of our polynomial function, f of x equals x to the fourth power plus x squared plus 1. Let's first identify the coefficients. We can see that the coefficient of x to the fourth power is 1, the coefficient of x to the fourth power is 1, the coefficient of x squared is 1, and the constant term is 1. Now, let's find the sum of these coefficients. 1 plus 1 plus 1 equals 3. Now, let's evaluate f of x at x equals 1 and compare it with our sum of coefficients. When x equals 1, we have f of 1 equals 1 to the fourth power plus 1 squared plus 1. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.